Hello, welcome back to the wonderful world of astronomy. This is Chapter 13, Other Planetary Systems, Part 2, Life Beyond Earth. In the previous video, you saw how many planets we've been discovering, exoplanets, planets outside of our solar system. And as of April 2026, that number was up to 6,273 confirmed exoplanets, and that number is always growing. They're always discovering new ones. And over the next years and decades, I imagine we'll be discovering thousands and tens of thousands of them. And so the question then comes up, is there life out there? Should we expect to find life out there? And I want to show you an example of a news article. Now, this was from CNN in 2020, and there's nothing particularly special about this news article. It's just the one that I found that demonstrates what I want to tell you. And I want you to, as an educated astronomy student, to be alert and aware and discerning of some of the manipulation that's in the media. So very often, if you see an astronomy-related article, probably the topic is on something out there, potential for life out there, maybe a planet out there that could have life. And there is this journalistic sensationalism where it's basically clickbait. They want to grab you at the title, and they often mislead you into thinking they've found something, maybe life out there or high potential for life. And this article gives a good example of this. So let's take a look at it together. The title of the article, New Potentially Habitable Exoplanet, is similar in size and temperature to Earth. Okay, let's just think about that title, how the title is crafted to draw you in, maybe with a little bit of manipulation. And so habitable, that means that life could exist on it. And that is actually the topic of this video, habitable planets. Exoplanet, okay, so planet outside the solar system. Similar in size and temperature to Earth. Why is that important? For a journalist to grab your attention? Well, because it relates it to us. It relates it to us, our planet. And it puts in your mind this idea of there is a planet that is like Earth that life could be on. Okay, now let's dive into the article itself. And the things that are in bold print and underlined, those are, I did that for emphasis. And so it starts with astronomers have uncovered a potentially habitable Earth-sized exoplanet. Okay, that's how it starts. Puts in your mind the idea that maybe it's a lot like Earth. It goes on, tells about the Kepler space mission. Let's go on down. The planet has been dubbed Kepler 1649c, so it's named after the Kepler mission. It's 1.06 times larger than Earth and receives about 75% the amount of light that Earth gets from the sun. Okay, so it relates it to, it's kind of similar to Earth. And now the bold print, again, my emphasis, bold print underlined at the bottom of the page. This suggests that the surface temperature of the exoplanet could be similar to Earth. Okay, before we go on to the next page, a discerning astronomer reading this article has already thought to him or herself, probably this is not a habitable planet. And it has something to do with the probabilities. Probably it's a red star, it's an M star. And there's something about red stars that make it very non-habitable for life. But let's drive on, let's continue. All right, continuing with the story, the planet is also located within the habitable zone of its star. Let me talk about what that means. Habitable zone is a phrase that means for any star, if you get too far away from it, it's too cold and you would have frozen water. If you get too close to that star, like Mercury or Venus is to the sun, it would be too hot and you'd have boiling water. So habitable zone is just the phrase that means it's a certain distance from its star where there could be freely flowing liquid water, because biologists have realized that you're going to need freely flowing liquid water in order for for complex molecules, carbon molecules, to come together and have life. So the habitable zone is just simply where the temperature is right to have liquid water. Um, let's continue reading. Existing at just the right distance where liquid water can exist on the surface. All right, I just said that. This also suggests that it could support life. And there's that phrase, it suggests. Well, what we're going to see in this video is there's a lot more to having life on a planet than just simply the presence of water. All right, here it comes. But Kepler 1649c orbits a red dwarf, much smaller and cooler than our sun. In recent years, multiple exoplanets have been found orbiting these stars that are common in our galaxy. The planet is much closer to its star than Earth is to the sun. Okay, why is that important for this discussion? Let's go down here. This also means that the planet could be lashed by radiation flares from the environment, threatening any potential life. Okay, so you've learned previously that roughly something like 80% of stars are red and orange stars. And these are stars that have these very dangerous flares. So what you need to understand is if a planet is in orbit around one of these stars, and think back to the Hertzsprung-Russell diagram, it's going to be low and to the right on the Hertzsprung-Russell diagram. It's dim and it's cool. And for the habitable zone, where there can be liquid water, that planet has to be very close to the star. And it would be close enough to where there's a lot of dangerous radiation flares that would be basically killing life or making it not suitable for life on that planet. So astronomers have decided that, and the journalist isn't going out of his or her way to point this out, that the majority of stars, of red stars, the habitable zone is not habitable at all because it's so close to the star there would be dangerous radiation. All right, so this is an example of what I call journalistic sensationalism, where they draw you in with a story about a planet that's been discovered, and they want to show you that there could be life here, to excite you about it, but most often, pretty much all the time, there's really nothing much to it. All right, so let's talk about the potential for life out there. It is a vast cosmos, as you've learned this semester, maybe 1 trillion galaxies out there. This is a picture from the Hubble Space Telescope. Every one of those bits of light that you see is a galaxy. So many galaxies out there, so many stars in each galaxy, and people say, certainly there must be life out there. We can't possibly be the only ones. And so when looking at that, when thinking about that, often people look at just one side of the equation. It's a big universe with lots of stars and lots of galaxies. But they're often not looking at the other side of the equation, which is what are the conditions necessary for having life? So we have science fiction with plenty of creatures out there and all these civilizations, but the question is, where are they? Should we expect them? And if they are out there, why haven't we come across even the slightest evidence for them? I want to look at some of the places that astronomers are looking for life currently. Now, we are currently looking in our own solar system. Not that we really think that there's going to be life in our solar system, but given that our solar system is as far as our technology currently allows us to get to, it's worth a shot. Just start looking around. And while I do think that's where nothing's going to come out of that, there is still good in the exploration, in learning about planets, how to get to planets, just learning about other worlds out there that will little by little add to our knowledge and our ability to get farther out into space. But so we are looking on Mars. And this is from 1977, the first spacecraft on Mars, the Viking 1 and Viking 2 spacecraft. And among other things, first of all, just to be the first spacecraft to land on Mars, and that's a pretty good achievement. But also looking around for life And when we talk about life, I kind of jokingly showed these characters from Star Wars. We really don't expect it's going to be these intelligent beings. We really expect if we find life, we're looking for microbial life, very small, maybe single-celled organisms. And that's one of the many things that these missions to Mars are looking for. And this is more modern for this century. We've sent a couple of rovers to Mars, and they do a lot of experiments on the geology, the soil, the atmosphere. But one of the things they're looking for is any evidence for life. And of course, we haven't found anything. So where else are we looking? Well, with a little less probability is the Galilean moons of Jupiter. Now, Jupiter is way out of the habitable zone for our sun. However, the moons show evidence, some of these Galilean moons show evidence that even though it's freezing cold out there, that there is geothermal energy under the surface, that under the ice there might be some warming, that energy from the center, just like Earth has geothermal energy. And they think maybe there's good evidence there's freely flowing water under the surface, and maybe we can find some evidence for life. And so there are missions ongoing looking for evidence for life on Europa and Ganymede, Callisto. And so those are the Galilean moons that we are currently looking at for life. By the way, let me insert here in case it hasn't become apparent. We have never found life out there beyond planet Earth. No life has been found. And so sometimes you'll read about evidence for the potential of life. And what they're finding is not life, but maybe complex carbon molecules, which is not at all life, but rather it is the building blocks that that if there are living entities, living creatures, they would use those complex molecules. But that's a long jump from actually saying there is life. All right, let's continue on. Saturn and Titan. Now, Titan is very unlikely to have life. But if we're looking around in our solar system, when we are confined to our solar system, we're going to look around everywhere we can find. Now, the deal with Titan, it is so far out of the habitable zone that there's not even going to be liquid water under the surface. But some astronomers think, and this is a huge long shot, thinking outside the box, but they think, well, there is evidence of rivers of flowing methane, CH4, on Titan. And they think maybe it's possible in ways that, life might work in ways we don't understand. Maybe it's possible for these complex molecules to come together, not in water, but rather in methane. Biologists don't think that's a possibility, but as I said, it's a long shot. All right, so if we're hoping to find life or evidence for life in our solar system, it doesn't look like we're probably going to find it. That doesn't preclude looking outside of our solar system, but the odds are going to be much better of finding life outside of our solar system, because that's where the vast cosmos is, all those trillion or so galaxies with all those stars. So astronomers are then thinking, where should we be looking as we scan the cosmos, as we're finding these new planets? What kind of places should we be looking for that might have life? Because we can't just look around the entire universe and hope to randomly spot life. It's just too big and too wide. So we have to narrow the focus to what kind of planets, what kind of places could we expect would be habitable. And so that gets us to thinking about our home, planet Earth, and what makes it so special. And what you're going to see in this video, it has a whole lot more to do than just having water. So let's look at some of the characteristics of Earth that make it special, that make it what one author has called in the title of his book, the privileged planet. We certainly live on a privileged planet, a very unique planet. I'm going to talk in this video about probably like 6 or 7 different characteristics. You should know there are more than 300 characteristics that make Earth special for life. And those characteristics had to be exactly in place the way they are for there to be life. I'm not going to go through all 300 plus, but just a few of them to give you an idea. So first of all, it needs to be around a star that is like our sun. And just remember as a refresher as we approach the final exam, the size of our sun in comparison to Earth. There we have the arrow pointing at Earth. The sun is about 109 times the diameter of Earth. But what is it about our sun that makes it special for life? Well, first of all, I want to talk about how chaotic and turbulent, violent the surface of the sun is, and there's a prominence that is much larger than the Earth. Of course, that's not the Earth's location relative to the sun, but remember, a lot of stars have these flares coming out from them, and so a planet needs to be a good distance away from its star. Now, this chart refers to the habitable zone, stellar habitable zone. And if you let's look at a yellow star like our sun at the top. And we move across to the right. And at about 1 astronomical unit, we see this is the distance it needs to be. And there's Earth in the habitable zone. Mars is barely on the other end of the habitable zone. And then we have orange stars and red stars bordering towards brown dwarfs. Maybe that's what this one is down here. But remember, those are dimmer and cooler, and so the habitable zone needs to be closer to the star. But remember, you get that close to a star, particularly red stars with a lot of violent flares coming from them, and the habitable zone, as I said before, is not habitable at all. And so we really need a hotter star like the yellow star that our sun is. This is a similar chart that goes up more into the white stars and the blue stars. And the habitable zone for those white and blue stars, so the O's, the B's, the A's, the F stars, the habitable zone is farther away, so you're going to be, if you have a planet there, it's going to not be so susceptible to flares, not being so close up. But the problem with that is those stars don't live very long. The hotter the star is, closer to the O's and the B's, and their small lifetime, astronomers are generally of the thinking that you need a long amount of time for the planet to have life, to be conducive to life. And so these stars just don't last long enough. They become stars, they're more unstable in their luminosity. They get brighter, they change in the brightness, and then eventually they will explode in a supernova. So astronomers generally are thinking we should be looking for a G star. And that precludes a lot of stars that are out there. What else do we need on a planet? Well, we need the right atmosphere, not just an atmosphere, but our life on our planet is so dependent on the entire water cycle. So the water cycle there, I have clouds above Pikes Peak in Colorado, but this idea that we have water in the oceans, water in the rivers and the seas, and the atmosphere brings it up through evaporation, forms these clouds, and then rains it down. And it's just this amazing thing that is necessary for life, the water cycle. You can't just have a stagnant atmosphere and water sitting on the ground and expect there to be life. There's a lot of complexity about the planet Earth just with its atmosphere that allows for life. So the planet, now I'm not saying that necessarily it needs to have a water cycle that goes exactly like planet Earth's is, but there is a lot of complexity in moving the water around properly to make life happen. It needs to be in a particular type of galaxy. a spiral galaxy. Remember, there are three types: spirals, ellipticals, and irregulars. Why a spiral galaxy? Why can't you have life in the other kinds? Well, if you remember back to chapter 19 and you think about the motions of the stars in the Milky Way galaxy, the central bulge, they're very chaotic, moving all over the place. And the central bulge is pretty much what an elliptical galaxy is. You have in the disk, the spiral part, that's where they're nice and orderly. We're not going to find life in the center of the galaxy, which also means in an elliptical galaxy, because there's just too much random motion, too much chaos. You have stars that are constantly moving by each other, pulling on each other one way or the other. You imagine a planet that's going around a star that's trying to have life grow on it, and the luminosity of stars in the sky keeps on changing. You've got radiation from all different directions that keeps on changing. And so you need a nice calm area. And you're not going to find that in an elliptical galaxy. You're not going to find that in an irregular galaxy. You're only going to find it in the nice orderly paths of the disk of a spiral galaxy. But it's not merely being in a disk that's needed. There's something called the galactic habitable zone. You're not going to have life too close to the central bulge, because that's where, as I described the central bulge in elliptical galaxies, you've got too much chaos, too much disorder, too much randomness, and a lot of radiation, a lot of supernova activity. You're also not going to find life out beyond the habitable zone because there's not enough supernova activity. Remember, chapter 17, it was titled Star Stuff. The meaning behind that title is that we, life, we're made of material that was formed inside stars. So we need supernova activity in our past to create the elements of life. So too close to the center and there's too much supernova activity, which would be very deadly for life. Far away, you don't have enough supernova activity to produce the right amounts of heavy elements. Now, it's not just in that habitable zone, but the same concept applies for whether in a spiral arm or between the spiral arms. And our sun is on the edge of one of the spiral arms. In the middle of a spiral arm, there's too much supernova activity. Right in the middle between spiral arms, there's not enough supernova activity. So astronomers think that in order to have life on a planet, that planet needs to be in a spiral galaxy, in the spiral galaxy's habitable zone, on the edge of a spiral arm. Astronomers believe that you're going to need a planet that has a single star, unlike Tatooine here in Star Wars. Going around two stars or multiple stars is going to cause too many changes, too much instability in the luminosity and radiation and heat that you get. So it needs to be one star. And remember, the majority of stars, slight majority of stars in our galaxy are in multiple star systems. So that alone gets rid of 50%, more than 50% of stars. This is a graphic of different planets that have been discovered, just showing habitable zones. I just put this in because I think it's pretty, but habitable zones, that there are some planets that have been found inside their stars' habitable zones, although most that we find are not in their habitable zones. The planet has to have the right amount of gravity in order to have life. Now, if we think about gravity and Earth's atmosphere, let's think first of all about what do I mean by the right amount of gravity? What causes gravity? Well, that has to do, as you think back to chapter 4, when you learned about physics and gravity, that the strength of gravity on a planet is determined by the size of the planet and the mass of the planet. More mass means more gravity. larger size means less gravity, so there needs to be this trade-off to give it a proper amount. Now, it doesn't necessarily, I don't think, need to be Earth's gravity, but there is just another variable in the complexity. It has to have the right amount of gravity that's going to be suitable for the life that's going to form on it. Now, let me show you what I mean. Earth has a certain strength of gravity, and we think about in the early atmosphere, when Earth first formed, there were a lot of gases in the atmosphere that do not exist. Well, they don't exist. I was about to say because they're deadly. Well, that's not why they're not on the planet, but we are thankful that they're not on the planet. Methane is one example. Methane, CH4, has a molecular mass of 16. And so that comes from the carbon has a mass of 12, and the four hydrogens each have a mass of 1, and so they add up to about 16. And so gravity was not strong enough to hold on to the methane, and so the methane floated away into outer space. Ammonia, NH3, that's pretty deadly, with a mass of 17. Gravity was not strong enough to hold on to it. And with just a little more mass, water vapor. Not only is water vapor not deadly, but it is necessary. We need water vapor in our atmosphere. And Earth's gravity holds on to it. So Earth's gravity let go the gas, the poisonous gas that has a mass of 16, the poisonous gas that has a mass of 17, but it held on to the necessary gas that has a mass of 18. So that's what I mean by Earth's gravity is just right. And so any planet that has life, again, I want to emphasize, I'm not saying that it needs to have exactly Earth's gravity, but this is just an example of these many things that had to be exactly right for there to be life on Earth. And so astronomers realize that for any planet to have life, there's a lot of things that need to be exactly right. What makes Earth special for life is carbon dioxide in the atmosphere. To the left, you see planet Venus. Way too much carbon dioxide for life. It has this extreme greenhouse effect. We need some carbon dioxide, but not too much. And so over on the right is just some pretty flowers indicative of all the life that is flourishing on Earth. There is the right amount of carbon dioxide that doesn't lock in, well, it locks in heat, but it doesn't overwhelmingly lock in the heat like Venus's atmosphere does. It locks it in pleasantly, so we have pretty stable temperatures, whether day or night, whether summer or winter. And we need that carbon dioxide. The plants breathe it, and they are, that's what I'll call the beginning of the food chain. So astronomers, when they consider all of the variables that go into having life on a planet, astronomers look at something called the Drake equation. Now, Drake was an astronomer, I think in the 1960s, who was contemplating the mathematical probability that we should find an intelligent civilization. So when he first came up with this, he wasn't actually looking at just simply life, like microbial life, but he was specifically thinking about an intelligent civilization beyond Earth. And so what he was thinking about was the question, how many life forms in the universe could potentially be discovered? And how many habitable planets should we expect to find in the universe? And he came up with this equation, and it's not a precise equation like some that I've shown you this semester. I see it more as a concept. And anyone who studies astronomy is familiar with the Drake equation, maybe not the specifics of what exactly are in it, but conceptually. The Drake equation is basically an equation for conceptualizing, for thinking about how many habitable planets should we expect to find in the universe. And it deals with the probabilities of if there's a random planet that we find, what is the probability that it'll have all the conditions be exactly right for life? So I want to introduce it to you. Please, unless you want to, don't worry about memorizing anything on this page, but it just gives you a sense of how this equation works. So N, Capital N, it's the number of planets that we estimate that are in the universe. And so you can think about probably 1 trillion galaxies. If there's about 100 billion stars in each galaxy, you multiply 1 trillion by 100 billion. And so if you then figure roughly on average 1 planet per star, and these are rough guesses, but you get a very, very large number of planets out there. But then we're going to multiply that. That's what these X's are. These are multiplication symbols. And we're going to get down to how many planets do we expect would not even have life, would be habitable, would be suitable for life. So we need to multiply the fraction by the fraction that have a single sun-like star. And so that might be 1/10 or something like that. Again, we don't even know these numbers. We make estimates based on our knowledge of astronomy. We're going to multiply that by the fraction that are in the star's habitable zone. And maybe that's about 1/10. You think about in our own solar system, not that that's enough data to go by, but we have 8 planets. 1 is in the habitable zone. You might consider Mars on the edge of the habitable zone. So maybe 1/8 or 1/4 would be that fraction for our own solar system. Times the fraction that are in a spiral galaxy. Well, if you make a rough estimate that 1/3 of galaxies are spiral, you're multiplying by 1/3. Times the fraction that are in that galactic habitable zone, times the fraction that have liquid water, times a fraction for all these different parameters. And every time you multiply by a fraction less than 1, the probability goes down and down and down. And remember, I've only mentioned maybe, 7 or 8, something like that. I think there's 7 on this page. But I said that there are more than 300 parameters that had to be right for planet Earth. This is a neat little exercise I came up with. I call it a 1 in a billion girl, the Drake equation, making it a bit more personal. And this would be neat to do. I do this sometimes in the classroom, but what I would really love to do is this in a stadium full of 100,000 people, a lot of people, and each person you can think representing a planet that's out there. But so I think about I'm looking for a particular person. So imagine we are in a stadium. We're at the center of the stadium with 100,000 people. And we get the stage, we get the spotlight. We say, I'm looking for in this stadium, is there someone who fits all of these necessary descriptions? And I'll just list them out as I see them there. A female born in November who's left-handed, drives a Toyota, at least 5'11", aged 40 to 44, whose last name starts with the letter V. Now you think about, if we're just talking about a female, is there a female in the stadium? Well, assuming it's all random, 50% of the stadium, so that's no problem there. Born in November, well, that cuts it down to about 1/12. If you want to be more precise, 30 over 365, because there are that many days in the year. Someone who's left-handed, I don't know what portion of people are left-handed. I've heard it's 1/10, but it's interesting. Now this gets into relating this to astronomy and thinking, what are the probabilities? We don't know the numbers to plug in. I say 1/10, someone else might say 1/5, but we're all kind of in the same ballpark. For born in November, you might have said 1/12, and that's fine. We're not going to be precise here, but it gets us roughly in the same ballpark. Drives a Toyota. I don't know. I did a little internet search on that for Americans, and it seems to be 1 out of 10. Maybe it's 1 out of 7. Maybe it's 1 out of 15. It's not going to throw my estimate off by that much. At least 5'11". Okay, so I looked this one up for American women, at least 5'11", and it was 15 out of every 10,000. And so I'll use that as the probability. But maybe you don't have the ability to look that up. Maybe you just want to guess, and maybe you would guess 1 out of 100, 1 out of 1,000. And that's what we do when we're applying the Drake equation to planets, looking for the right parameters, everything to be right for a planet with life on it. We make educated guesses. Age 40 to 44, I think I looked that one up as well, about 6 out of 100. Last name starts with the letter V. Yeah, I looked that one up too, 26 out of 1,000. When you multiply all those fractions together, you get a probability. The probability of finding such a person randomly, you just randomly pick someone out of a crowd, is 1 out of 1 billion. And I've only looked at 7 parameters as it applies to people, but 1 out of a billion. That's why I call this little exercise a 1 in a billion girl. Now, what that means is if I were in the middle of a stadium full of 100,000 people, I would expect that not a single person would fit this description. Now, that doesn't mean I would bet all my money on it. There might be one person, might be 2 people, but the odds are in a stadium full of 100,000 people that not a single one would fit the description. In fact, over all the planet Earth, there's something like 8 billion people, maybe approaching 9 billion, something like that. I should only expect maybe about 8 or 9 people to fit this description. Now, this relates to looking for a planet. We have trillions upon trillions of planets out there just waiting to be discovered. But when you put together all the probabilities of every characteristic being exactly right to have life, it is way lower probability than finding a 1 in a billion girl. The probability of finding, I mentioned these 300 plus parameters. Astronomers have found, last I looked up these things, 332 different parameters, things that need to be exactly right, whether it's going around or being in a spiral galaxy, going around a single sun-like star, being in the habitable zone for that star, 332 parameters. And using the Drake equation, astronomers have estimated that the probability is not just 1 in a billion, but 1 in 10 to the 304th power. Now think about what that means. A billion is 10 to the 9th power, a 1 with 9 zeros. This is a 1 with 304 zeros after it. That is a mind-bogglingly low probability. That reminds me, I haven't done the calculation, but of something reminiscent of the probability of all the air molecules in the room you're in, all moving to one corner of the room all at once, because they're all in random motion, but all just randomly moving to the corner of the room and suffocating everyone who's in the room because there's no more air for them to breathe. This is a probability that physicists, when they deal in probabilities, would just call this 0. Physicists would look at this number and say, that's a 0 probability. But mathematically, 1 in 10 to the 304. Now, the maximum number of possible planets in the universe, again, this is an estimate. Astronomers are generally agreed it's about 10 to the 23rd power, 1 with 23 zeros. Where do we get that number? Well, if you take a trillion galaxies, estimate about 100 billion stars per galaxy, estimate maybe 1 star, you could even be more liberal with it and estimate 10 planets per star, but the numbers come out to be about 10 to the 23rd planets we estimate in the universe. But that number is so small compared to the probability that you see up at the top of the screen of one planet having all the conditions right for life. So the probability of one habitable planet existing is 1 in 10 to the 282. Such a small number. This is a probability that, again, physicists would look at this and say that's a 0 probability. Now, I'm not talking about that this is the probability of one planet out there somewhere being habitable. This is a probability of one planet anywhere in the universe being habitable. The probability is essentially 0. And yet, and here's the big point here, we are here. Earth is here. Earth exists as a planet with life, totally defying the mathematics, the random probabilities. And so, could there be another planet out there? Sure, I think so. And the reason is because we shouldn't even be here. So it seems to me that something is defying the probabilities. Just to give you an idea, what is the probability 1 in 10 to the 282? It is the same as the probability of flipping a coin 936 times and every one of them ending up heads. It's roughly the probability of winning the state lottery 41 consecutive times. Now, at some point in either of those, if you were to do those experiments, whether playing the lottery or flipping the coin, at some point, someone's going to realize, hey, this is rigged. If you flip a coin, you get heads, no problem. You flip it again, you get heads. No one's going to think anything weird of that. You flip it a third and fourth time, and it keeps landing heads. About the fourth or fifth time, people are going to start to get suspicious that that thing is rigged. Same with the lottery. If you keep winning the lottery day after day after day, people are going to get suspicious that there's something non-random about this. And this brings us back to many of the Renaissance scientists like Nicholas Copernicus, Galileo Galilei, Johann Kepler, whose motivation to study the universe was a motivation to learn about the Creator. Nicholas Copernicus, in his famous book on the revolutions of the heavenly spheres, he said, "The universe has been wrought for us by a supremely good and orderly Creator." And so that's what this evidence is leading to. The fact that we have a planet that is conducive to life, that everything had to be just right to make it that privileged planet. And not only that, a variable that I haven't even gotten into in this video is that there is life and life in abundance, gives a lot of evidence for that this has been created. And so I'll repeat, as Copernicus said, the universe has been wrought for us by a supremely good and orderly Creator. And I'll end with just a quick little bit on the Arecibo radio telescope in Puerto Rico. Astronomers have been gazing at the skies, looking at the skies with radio telescopes to see are there any signals, any evidence from alien civilizations. And this is one such telescope, the Arecibo radio telescope. And so astronomers are looking passively to see, are there any civilizations out there that we might make contact with? And as that SETI, which is the Search for Extraterrestrial Intelligence, as that has been going on for several decades, haven't found anything yet. That concludes this video. Have a great day.